Okay, so welcome to this course on algorithm design and analysis. And many of you, all of us have seen algorithms um, starting from high school, where we learned how to multiply numbers, how to find the GCD of two numbers, multiply matrices, find the square root of a number. All of these are algorithms we have learned throughout our life in starting from school level. And what we are going to do in this course is to take a little systematic attempt at designing algorithms. We learn some new algorithmic techniques. We will analyze algorithms. We want to see the efficiency of an algorithm, and once you measure and analyze an algorithm, we want to think in terms of coming up with better algorithms, right? And one of the things, as particularly all of you are mathematics students, we will also be worrying about correctness of the algorithm, right? It's not just enough for your algorithm to be efficient, but you want it to be correct, and it means it's expected to do whatever it's expected to do on all inputs. So this is one of the things we will be emphasizing it, but we certain algorithms are easy to prove correctness, certain algorithms are not, and we may not be very consistent about spending time on trying to prove correctness, but it is important for you to know that you need to prove correctness of the algorithms. Okay. For some of them, it's fairly obvious. For some of them, it may require some work. So we will be worrying about correctness, designing algorithms. So we will learn a bunch of techniques, and we will be analyzing the efficiency of algorithms, mainly because it's think of algorithm design as some sort of a job of an architect in trying to construct a building, right? So before you design any software, you want to design your algorithm. You also want to measure and analyze it for efficiency, because often you may not be able to afford to go and implement and see how fast the algorithm runs, what sort of memory it's using and all that. We want to do a more theoretical analysis in a model which is realistic in practice as well. Okay, so that's the kind of things we'll be doing. And so I expect some knowledge of programming. So by the way, I don't know whether the system works that you can ask. Can you also ask me questions? Do you have a mic or something by which you can interact? Usually it works, but I hope it does. Okay, so you can also ask me questions, right? Right, okay, good. So I expect some knowledge of programming, because especially when I talk about for loop, while loop, or if then else, some, because we will be looking at in no specific programming language, but we'll design algorithms in a programming language independent way. And some of the things you learned in your discrete math course and combinatorics and graph theory will be very useful here. So in particular for you mathematics students, I would say this course is a real gateway to computer science, where you can actually apply some of the mathematical techniques you have learned. And it also, algorithms is the core of computing. So everything in computer science depends on algorithms. So this will be opening you doors. So and it also will be largely a problem solving course. So we'll be designing algorithms for a bunch of problems, trying to design more efficient algorithms, and so on and so forth. Okay, so a knowledge of programming is useful, but no specific programming language is necessary here. Okay, so we didn't really discuss about what is an algorithm. Again, one can define formally using Turing machines, a model of computing, but it's just a sequence solve some computational problem, and it is operating on some data and which is accessible in a particular way. Okay, many of these things we will fix things as we move along, and so one of the things as we will do is also we will look at efficient ways of organizing your data to design your efficient algorithm. So data structures is another part of the thing. So we'll look at some basic classical algorithms for sorting, searching, selection, some basic graph algorithms, and we learned some algorithmic techniques like divide and conquer and dynamic programming, greedy, and some of them. And one other thing which is important is that you need to know whether you've reached your limit on designing your efficient algorithm, right? So the goal is to design better algorithms, but what is the limit? How far can we go? And can you somehow argue that for this problem you cannot do something better than this? Okay, so that takes us to this notion of, is there some sort of a lower bound for the problem, lower bound for the time taken by any algorithm for this problem? Okay, so this is a hard thing, and these are some of the aspects we'll be covering it through this course. Okay. All right, so I will start with a specific problem, and we will look at a couple of algorithms for the problem and see why efficiency in algorithms is an important thing. Because one question you should ask is that nowadays computers are all powerful, they can do crunch millions of instructions in a factor of microseconds and stuff. So does it matter that you need an efficient algorithm for a problem, right? So let's try and see the contrast. And okay, so there are a couple of standard books I will be so one is this algorithms, I don't know what the actual title is, was Carmen's book, Introduction to Algorithms or something, by Carmen Lysersen Rivest and Stein. And there is another one by, this is Kleinberg and Tardish. In fact, there are several. I mean, several standard modern books. The bulk of the material they'll be covering is the same, which we will cover. Each one of them will have slight differences in their style or some additional topics they may be covering. But along the way, I will give you some references for anything where I am looking at covering from. Okay, so let's start with the following problem. So you have two large arrays. Okay, let's call them A and B. So I think containing some let's say some numbers. The key thing is it's large. Some n numbers. Okay, so n is large. think of it as in the order of something like 10 power 10. Okay, so maybe your Aadhaar database or something like that. Okay, there are 125 million population, right? So 100 million people have Aadhaar numbers. So think of this as some Aadhaar database, two of them, SIM card, land registration, some huge database. And this a problem we want to find. So these are some array of numbers. So you all understand what an array means? Yes? No? Okay. Think of it as a large sequence. Okay. You're a mathematics student, so you'll know what a sequence is. So array is some sort of a very basic data structure, but it's just a large sequence where I can go and access ith element of the sequence in constant time. Okay. So this is good enough for our purpose. Now, the problem I want to solve is find all common entries between A and B. So maybe create another array C I want to create another large array C, maybe large, maybe small, I don't know how many are common, but I want to create an array C where I want to put all the common entries there. Okay. So what would be an algorithm for this? So anybody wants to suggest something, for loop, while loop, or you just say it in English, doesn't matter. So how, I just have these two large arrays and I want to find all common entries. So what would be a systematic algorithm? Yes, go ahead. Yeah. Exactly. So can you say it in a like a program? What sort of a loop would you use? Yeah. So for I, let's say going from 1 to n, because n is the total number of entries in A, right? And then yeah, okay. So okay, let's write. So if AI, for now, let me write it like this. We will expand it later. Then something like C of K would be A of I. Okay. So and I'm going to increase K. Okay. So K is some output array which is initialized to 1, and then for going from every entry in I, if I find AI in B, then the next available index in C, I put AI there and increase K. Okay. So now this is exactly the way I would write algorithms, right? First of all, in a very high level, we write something like a little bit of a programmed English kind of thing, and then gradually we want to make it closer to a program. So one reason we want it to be completely well specified is that that's when you can actually analyze an algorithm, right? If I want to know how efficient or how many steps the algorithm is taking, you really want to make sure that there are no ambiguities and you write down all the details, right? So how do I check if AI is in B? So another loop, right? Exactly. So what is another loop? So I'm going to say for j going from 1 to n, what do I do? If AI equal to bj, then, okay, so then is here. Yeah, so now this is more or less a complete well-specified algorithm. So what it's doing is that for every entry, ith entry in A, it's just running it over all values of B, and the moment I find something equal to that, I'm just going to output in C. Good. So now let's analyze this algorithm, right? How many quote unquote steps the algorithm takes, right? Well, how do you analyze it? We'll just see what are the things that's happening. Yeah. N square steps, right? Okay, good. Because essentially, if you look at how many times this step is executed, that is like n square, right? Because for every I am running it over all possible things. So this is like n square steps. There are more things happening here, but this is the dominating thing. So this is n square. So this is like an n square algorithm. But n for us is like 10 power 10. Okay. So this is for our value of n, this is 10 power 20 steps, right? 10 power 10 square. 10 power 10 square is 10 power 20, right? Okay. Not 10 power 100. Okay. So now, so your modern computer, like your laptop or whatever you have, the most powerful thing, how many steps do you think it can do in 1 second? It can do something like 10 power 10, okay? About a billion instructions per second. So, if I assume that this computer can perform 10 power 10 steps in 1 second, then how many seconds will this algorithm take? Yeah? Okay, good. You won't believe I've tried this at several places. People have said 2 seconds. Okay, so anyway, so you all agree that this will take 10 power 10 seconds. Which means how many days, how many months, how many years? If you Google out, you will see that this is about 330 years or so. Okay, so this is a simple calculation. You know how many seconds are there in a year, and you divide it. So this is about 330 approximately years. Okay. Now you don't see this when you actually go and implement a simple algorithm in your assignment or your lab. Why do you not see this? Because you will work on small data sets. Your data sets, because if your data set is so large, there will be other issues, some caching issues and so on. But typically, you might be looking at a data set of 1,000 or 10,000 for which, so if the data set is like 10 power 5, then n square is 10 power 10, which will take you 1 second. Okay. But we are talking about big data, right? We are talking about computerizing everything, and so other numbers and so. So on this kind of a thing, this n square algorithm takes you about 300 plus years, which is not useful at all. Okay. Okay. So what can you do? Suppose somebody tells me that, hey, this array B is arranged in increasing order. Okay. So this is the same problem. But suppose I tell you that array A or array B, the numbers are in increasing order. Now, right, this question, what was this question? It was if AI is in B, right? This is what we wanted to do. You wanted to check if AI was in B, and this was the way we expanded it. But now if I tell you that my array A is in sorted order, can I do better? What can you do? Items not in B but in A. How do you check that? How do you find that? In log n. I want to know how first. What will you do? What will you do? What is your algorithm? So I want to know whether AI is in B. How? Yes. What do you do? Binary search. Does everyone know what binary search is? Good. I mean, can I have a show of hands? People who don't know binary search. Okay, good. So let's go through that. Okay. So if the array is sorted, turns out you can do much faster than checking for an element in that. But so what was this algorithm doing? If I want to know AI is in B, it was just checking at each entry in B whether, is it equal to AI? Is it equal to AI? Is it equal to AI for every entry? And it took us n steps. But now, how can I take advantage of the fact that B is sorted? And the suggestion is that do what is called a binary search. So let's keep this in mind. So because we need to solve this. So this n squared steps was our simple algorithm, which was 10 power 20 steps, which is about 330 seconds. Okay, because I want to do this. 330 years. I want to do a comparison with our algorithm. So what is binary search, right? Okay, so the simplest way to explain this is like, suppose I think of a number between 1 and 1,000. And your job is to ask me questions to find the number. And how many questions do you need? Okay. So, is the problem clear? So we'll come back to searching in a sorted array later. So suppose I think of a number between 1 and 1,000. Okay. And the game is that you have to ask me questions to find the number. And what is the minimum number of questions you need? Okay. So what question would you ask? You can ask anything, right? Yeah. Can you actually find my number by asking me only one question? What is the number? Why don't you ask me that? Okay, and then I'll give the number, right? Of course. Because I will hold my promise that I won't lie. Okay, so so now actually no. So the real game is that I will answer only yes or no. Okay, so you have to ask me questions and to find the number by asking me yes or no questions. Now what would you ask? Greater than or less than 500, I'll say yes. Yes. So you have to make your question precise. Is it greater than 500? Okay. And okay. So now you all got the game, right? So, and if I say yes, what will be your next question? Greater than? Right. So you see the game. So what are you doing? What is your next question? You are dividing the range. So when you ask me, is the number greater than 500? So initially, what are we trying to do? We are playing the game of reducing the range, right? My range. I had 1,000 choices initially for the number to think of. But the moment you ask me one question, it doesn't matter whether I answered yes or no. The range has come down by a factor of 2. If you ask the question, is it greater than 500? Right? Because if you ask the question, is it greater than 25? I would say yes, then you've not reduced the range so much. Right? So, this algorithm of asking exactly in the middle, right? So you ask the question. So let's make life simpler. I don't know simpler, but suppose I think of a number between 1 and 1024. You ask, is it greater than 512? And I say yes. Then you ask, is it greater than 768? I say no. Then you know that the number is in the range 512 to 768, right? The key thing is that there are only 256 numbers here. So in one question, you've reduced the range from 1024 to 512. In another question, you can reduce the range to 256. In another question, if you do the same game, you will reduce the range to 128. So how many questions do you need in this algorithm? Remember, this is a specific algorithm you are playing, which is ask in the middle. How many questions do you need before you can pin down and get my number? Right? So, for 1024, how many questions do you think? Or let's play with a smaller, much smaller number. In fact, one way I play this game is that think of my date of birth, right? So that's a small number. Let's say I'm thinking of a number between 1 and 32. So in one question, the range becomes 16. One more question, range becomes 8, 4, 2, and then you ask one more question. You know exactly what number I'm thinking of, right? So in 5 questions you can find this number between 1 and 32. What about for n? How many, if you play the same game of asking in the middle, is the number greater than this or less than this? How many questions do you need? Yes? Yeah. Does everyone get that? And where is this log coming into the picture? First of all, log n may not be an integer, right, to the base 2. So it's more like round it up. So I'm going to put this, I don't know whether you've seen this. This means round it up. You may need to ask this extra question. So you see why log n is coming? And how do you even figure this out? Well, any ideas? Why log n?
Because each step we divide into 2 hours.
Okay.
As we are dividing the
So
range,
there are some students here also. I'll yeah.
as we are dividing it into 2, so we are effectively reducing it by half. So as each step we are splitting into two, the base is
There's still something missing. So the answer is that, oh, we are dividing the range by a factor of 2 every time. Hmm. Right. So exactly. Okay. So let's see. Well, let's do this for general n, right? So if I had n in the range after one question, my range will become n by 2, right? Ceiling n by 2, whatever, because n may not be an even number. So that means let's round it up. If I make two questions, my range will become n by 4, which is n by 2 square. And if I do three questions, my range will become n by 2 cube. We will actually formally analyze it later, but I just want to go through and see the comparisons for now. So if I do k questions, my range will become n by 2 power k, right? So when will the algorithm stop? When the range becomes 1, right? So when this becomes 1, then you know you found my number. You have guessed it correctly because there is only one choice consistent with all the answers I've given. So what does n by 2 power k equal to 1 means? What is k? 2 power k is n. If you take log to the base 2 both sides, so that's this. Okay. So in other words, log n is essentially the number of powers of 2 in your n. How many powers of 2 is there in n? That's what is denoted by log n. This is exactly the definition of log n. How many powers of 2? What is the highest power of 2 you have in n? That's log n. Okay. So, and then you're going to keep seeing log n in many places in algorithms as we go along. So, and usual trick to get this log n is that you somehow, if you can reduce your problem size by a factor of 2 every time by making one step, then you are getting log n. Okay. Okay, but let's turn around the question, because this is just, this is not for the purpose of our comparison, but just for fun. Suppose I want to force you a lot of questions. Okay. Then what number should I think of? Okay, so let me phrase the question again. I think of a number between 1 and n. You are going to keep asking me these yes or no questions and you will guess the number. I don't know what question you are going to ask. You may or may not necessarily play binary search. By the way, so this algorithm is called binary search, and we will see again and again in multiple situations. So you may not be asking binary search. You may ask arbitrary. Is the number prime? Is it divisible by 243? I don't know what you will ask. You are allowed to ask any yes or no questions, right? Now my job is to force you to make a lot of questions. So what should be my strategy? Okay, remember, this is a lower bound question, right? I want to say that this is the best algorithm. Binary search is the best algorithm in some sense. Somehow, if you do anything else, I can force you more questions. So, what should be my strategy? What number should I think of? What should be my strategy? Hmm?
choose the
Yeah.
block or the range in which it has large.
Yeah. So, okay. Any ideas from there? N minus one. Huh? Sorry. Remember, I don't know what algorithm you are going to play. So, the answer is that I will not think of a number at all. Because whatever number I think of, you might ask that as a first question. How do I know, right? So, so I will keep my options open. Based on the question you ask, I will give you a number. So what is my, so that's why I said what number, I didn't ask what number should I think, what should be my strategy. But at the same time, I have to answer, right? I can't be rambling about it and I have to be consistent with whatever I've said. So what do? Remember, the game is about reducing the range, right? Initially, I have 1000 numbers. So suppose you ask the question, is the number greater than 37? What should I say? Yes, right? Remember, I haven't even thought of a number, but you all figure out that the strategy for me is that I should answer yes, right? I will quickly go ahead and pick a number in range 37 to 1000 and keep that as a possible choice. I won't fix it because next time you might get that number. So the strategy is that whatever range is bigger, I will answer accordingly, and finally I will be able to give you a number because I will say this is what I thought of. Look at the answers I gave you. It's consistent with all that, right? So this is sort of lower bound. We'll come back to it later. This is called an adversary strategy to prove lower bounds. We'll come to that later. Okay. So now, what has this got to do with the problem we started off? Like we have these two large arrays and we need to figure out whether B is in the sorted array A. Can we use this idea to somehow speed up the search for checking whether this array B is in? So remember, our algorithm is for I going from 1 to n, check if AI is in B, and if S, then we have some Ck equal to AI, K going to K plus 1. So now, if somebody told me that B is already in sorted order, in increasing order, can I now do this search faster using this idea of binary search, right? This. So what should I do? Yeah. Right. So I have this array B. I want to know whether AI is in the list, but I know that it is in increasing order. So what do? I compare AI with the middle element of B. Okay. Then either it may be equal to or less than or greater than. If AI happens to be less than Bn by 2, then I know that I don't have to search here because AI itself is smaller than this. Then all these guys are going to, no, sorry. Then I know that I don't have to, if AI is less than Bn by 2, then search in B1 to n by 2 minus 1. Because AI is small, there is no way it's going to be in this portion of the array. AI is already smaller than this, so it's going to be smaller than all these guys, so no need to search here. Else, if AI equal to Bn by 2, then sort of output and else search in B n by 2 plus 1 to n. If AI happens to be bigger than this, then I know that it's going to be only here. Right? So this search in and all that is, you can, how do I search in that array? Sorry? No. The middle element of that array, right? So this is basically apply the same algorithm, and there is a word for it which is very useful. It is basically, it's called recurse, right? Which means apply the same algorithm. Right? So we're not going to just go and search one by one. If you say search in 1 to n by 2 minus 1, I'm not going to search one at a time, but apply the same algorithm means that I'm going to search in the middle array, middle portion, and then continue. And that's, or in this case, I'll apply search in the middle portion and continue, right? Right? So now, how much time does this algorithm take? How many comparisons will you perform the AI, some entry of A and some entry of B? By the argument we just went through on this game of guessing the number, every time your range decreases by a factor of 2, so you will make log n many questions for each such, right? So we will again go through all this carefully, formally, we'll write what is called a recurrence relation and do all that, but I just want to give you a flavor of why algorithms are important and what we are going to encounter in this course as we go along, right? Good, so we had one simple algorithm, now we have improved it by, with the extra knowledge that B is arranged in increasing order, that we can do this in log n many comparisons. Now the overall amount of time we have spent is n times log n, right? Right, some ceiling. Right, the earlier algorithm which was doing linear search was n square, but now by just observing the fact that we can do binary search on a sorted array, we have made it to n log n. Now let's do our calculations. What was n? 10 power 10, right? So this would be like, so it will be 10 power n, 10 log n, which is log 10 to the power 10 to the base 2. So what is log 10 power 10? By the standard log formula, it's 10 power 10 into 10 log 10. Right? Log A to the B is B log A. So what is log 10 roughly? 3 point something. Does everyone see that? Because as I told you, what is log of a number? It is how many powers of 2 is there in that number, right? 2 cubed is 8, 2 power 4 is 16. So in 10, the power of 2 is like 3 point something. So I will even make it 10 power 10 into 4 into 10. Remember, this is the number of steps. But how many seconds? 40 seconds. Right? Quite dramatic, right? Remember, the n square algorithm was taking 330 years. And n log n is just like 40 seconds, right? I mean, so now sometimes when you run some program and it's taking ages, you might blame it on the internet, you might blame it on, oh, maybe there is an infinite loop. No, 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 no. Maybe there is an n square algorithm which will take 300 years. Okay. So, and the problem changed tiny bit, right? Remember, this was not the original problem. What was the different problem?
Finding
The same problem, but there was something special about the input. We assume that B is sorted, right? So now you should ask the question, if B is not sorted, how much time does it take to sort B, right? Because that should not take 330 years. Then there's no point in this game. Okay? So now, is it clear? So now that takes us to the next topic which we want to talk about, which is sorting. Okay? So let me summarize again what we did. So we had a simple problem, two large arrays, we want to find all common entries. A naive algorithm will take n square time, but if one of the arrays is sorted, then we can use binary search to reduce the running time to n log n, and it makes a big difference for large values of n, especially if n is like 10 power 10, then n square n log n is not just a tiny improvement, it's between 3 centuries and 40 seconds, right? Okay, so now let's start. Okay, how fast can you sort, right? Because it crucially required, the whole thing required the fact that you have kept somehow one of the arrays in sorted order. Okay, so this is dramatic. I mean, people have seen this. Now, later on in the course, we will see that there are problems for which, forget n square, we don't even have n power 10 algorithm. Okay, so for those problems, you don't even have to go to 10 power 10 to see the difference. Even in the order of 10,000, the difference will show up. And now I also want to throw you this idea of this asymptotics, right? We really want to compare algorithms and analyze them as n increases. As input size increases, how does the behavior change, right? Okay, so this is an important problem where you want to arrange a given sequence in increasing order. Or decreasing order. Okay, they're all the same. And I mean, we saw why it is important, right? Why is it important? Because why do you want to keep your array sorted? Why? It's easy to search, right? Just imagine if the dictionary is not sorted, right? how do you search for an element? Of course, nobody takes the book and now everything is online, but it's the same story there, right? So in fact, there are some studies that show that some 30-40% of the computer time is spent on sorting. And anything, moment you computerize some data, the first thing you want to do is to keep your data sorted, because that's what helps you to search, right? So it's important to learn efficient sorting algorithms. And of course, sorting is something you've seen from grade 5, grade 6, where kids are given some numbers, arrange it in increasing order, decreasing order. But we want to find some systematic way, analyze the algorithm, and more efficient algorithm. Okay. So let's take the simpler problem of finding the max. Okay, so we'll come back to sorting later. So this is like, suppose I want to find just the maximum of the given list. So what would be an algorithm to do this? Yes, so let's say again an array A is given, an array of numbers, and I want to find the maximum in the list. Hmm?
If it is sorted, the first or last element. If it is unsorted, we need to check every element.
Binary search to sort, to find the max.
The first or the last element, according to the increasing or decreasing order.
Yeah, so the array is not sorted. I want to find the max.
Then pick the first element, compare it. If the element which occurs later is greater, drop them.
Initialize the maximum element as given every time you go through the array to see if it's larger than the greater than.
Okay, so a suggestion here was, let's say your array is A, so I want to initialize an element called max, which I'm going to assign it to A1, right? And then I have a for loop which simply says if ha. And finally, what is stored in the variable max is the maximum element, right? So for a while on sorting and these kind of problems, we will be focusing on this kind of a operation, which is called the comparison operation. So how many comparisons are made in this algorithm? Not really. How many? N minus 1 comparison, right? Okay, so first question is, is there a better algorithm? Can you find the max? Again, remember, this comes to the lower bound question. We will not do lower bounds too much because lower bounds is hard and there are very few known about it. But this is a topic problem, so let me throw the lower bound question. Is there an algorithm which can find the max in better than n minus 1 comparisons? Why not?
Because to check every element, we need at least n minus 1.
Why?
If we just have an algorithm if we have an algorithm which requires only n minus 2, then we will be checking only n minus 1.
No.
At most n minus 1.
Okay, so the argument is that you have to look at every element, but n by 2 comparisons are enough to look at every element.
To check with a particular element.
Because I just pair them up and compare. If you really say I want to touch every element,
Yeah, you take two and have the largest from them and then.
no. I'm just saying that if the argument is, oh, you have to touch every element, you have to look at every element, I'm just saying that's not a good enough argument because n by 2 comparisons are enough to touch every element.
We need to compare particular element with remaining element.
I don't know. I mean,
Even a big array can be like split the array and sort this and sort this and
sort this. That's a heavy
half array.
task. I mean, it's going to take much more than.
Like we are sorting a big
Yeah,
array.
go ahead. Yes, please. Yeah.
So I was thinking we could apply some logic like binary search here. So we have to find the max of n numbers. We could start by finding the max of 1 to n by 2 and n by 2 to n. And no, just the array element. And then that we could find by finding the max of the 4 parts of it and compare those.
Okay. That's you. That's a useful thing, but I mean, nothing else. It will help you understand binary search better now. The important, the important thing about binary search is that after one comparison, we only looked at one half of the array. We just threw away one half of the array. But now here what you are saying is, I'm going to find the max in this half and find the max in this half. So you're keeping both the arrays. So not going to be easy. Okay, so it requires more work. Yeah, but suppose somebody tells you that I can find the max in log n comparisons. Can you believe it? Is there your kind of an argument will work? Right? Somebody tells you that I can find the max in log n comparisons. See, you have to look at every element. That's important, right? I mean, you've not even looked at some element. Log n is a much smaller. We saw that. Log of 10 power 10 was only about 40, right? So you have a billion numbers. Suppose somebody says I can find the max at 40 comparison. That means you have not even looked at a large portion of the array. How can it be true, right? Clearly,
You can pair them up, get the maximums, and within the maximums again pair them up, get the maximums n by 2 and then n by 2.
okay. So here is a different algorithm being proposed. Let me write the algorithm and we'll see what happens. So what she is suggesting is how you would organize a tennis tournament. Let's say a knockout tennis tournament, right? Suppose you have 15 players or 16 players and you want to organize a knockout tournament. What does knockout tournament mean? That if they lose the game, they're out, right? How would you organize it? It's the same as finding the max in some sense, right? So, same, okay? We'll see how that is, okay? So the algorithm is you take the first two numbers, compare them, right? This is how you will organize your knockout tournament, right? There are 16 players. You pair them up. You pair them up into 8, and so the winner moves to the next round. The loser is out. Let's do it 8. It's easy. And then you pair the next round players, and then you pay the finals. Whoever is winner is declared as the winner, right? That's a max. That's it. First of all, remember I mentioned about correctness. design analysis, so we need to prove that this is correct. Clearly, whoever is declared max is the max at the end because everybody else has lost some game, which means they are smaller than somebody else, right? Everybody else has been defeated at least one game, so they are all out. So only one guy survives. So the person who survives is the max. So this is the proof of correctness. Okay. Now let's see how many comparisons we would have made. In general, is the algorithm clear? I pair them up. There are n players. Let's say n is a nice number, power of 2 and all that. We'll come back to if not later. N is a power of 2. So you can keep dividing by 2, that's not a problem. Now I pair them, right? All the winners go to the next round. Pair them up again. All the winners go to the next round. Eventually there will be one player surviving. Think of it as a game. Think of it as a comparison between two numbers, two entities, AI and AJ. And we have found the max. How many comparisons have we spent? Yeah. So how many comparisons totally? How many comparisons in the first round? N by 2, right? Because there are n players and I paired them up, so I got n by 2 games. Next round, n by 4, and then you have n by 8, and eventually you got 1. So let's say I said n is a power of 2, so let's assume n is 2 power k. Then what I have is 2 power k minus 1 in the first round, plus 2 power k minus 2, plus 2 power k minus 3, plus da 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 da, plus 1. This is a geometric series. What is the sum? 2 power k minus 1, which unfortunately is also n minus 1. Really, it's not. We had the same n minus 1 comparisons even on that algorithm. This is another algorithm which number of comparisons made is n minus 1. Now I'll let you think about why you cannot improve it. Okay, there's an argument. First, I mean, you need to think about how do you even model such a statement, because you're talking about no algorithm can do better, right? Somehow you need a measure, a way viewing any algorithm. We did this for binary search. We had this adversary, right, which was sort of what do I keep? There is a number for which I will force you log n questions. That's the kind of argument we had. So something like that you can argue here, that you cannot do better than n minus 1 comparisons to find the max. Okay, but that's somebody who is challenged enough to think about it, fine. But let's come back to we'll stick to designing algorithms. So we can find the max in n minus 1 comparisons. Given a sequence of n numbers, there are a couple of algorithms we came up with where in the worst case we can find the maximum in n minus 1 comparisons. Now can I use it to sort n numbers? Use this as a subroutine. So now my goal is to sort, right? Arrange everything in increasing order, and I have a subroutine which simply says find max. You give an array, it will give you, return max. Can I repeatedly use it and design a sorting algorithm? What should I do? How? Keep finding the max in your smaller and smaller arrays, right? So first I would say an I'll replace it by whatever I get find max in the array 1 to n, right? And when I do that, I'm going to swap. So I have my array A, I find the max, you know how to do it in n minus 1 comparisons, put it here, and wherever max was, I will swap it with whatever the current last array, and then give the find max algorithm this array, right? After swapping an and ai, this was the max index, right? So I can keep doing this, and eventually I will have my array sorted. Is that clear? And you can prove correctness of this algorithm because I found the max that was correct and put it in the last position, and whatever should occupy the next last should be the max of the remaining elements, and that's exactly what I did. Okay. So is the algorithm clear? And you believe it's correct? Now how many comparisons have we made so far? The overall. Exactly. So n minus 1 plus n minus 2 plus n minus 3 plus da 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 plus 1. You know the formula for it? So this is roughly n square by 2. Okay. So if you use this to sort our big array B, it won't take you 330 years, but it will take half of it. Okay. 100 and whatever, 65 years. Some consolation, but it's still pretty bad. So now I want to think of better algorithms, right? So again, we will try and use this divide and conquer kind of an idea. Yeah.
It should take more than 165 years, right? Because pi max itself will have the complexity of n minus 1.
Yes. So what? Sir, what? It should take what?
So we are finding the max and making comparison.
Now we are finding the max, that will take you n minus 1. And then we are finding the max of the remaining. That will take you n minus 2 and n minus 3, and that's how we got this. Okay, so if I want to do, we don't expect to sort in log n time or something, right? Clearly. I told you, I can't even find the max in log n time because you have to look at every input. Clearly, this is sort of a common sense kind of a thing. You should see that any algorithm to sort should take at least n comparisons. At least it should take more than n for sure. You can't do anything better than n because you have to look at every input, do some comparison, so on. But I want to improve from n square. Okay. And somehow using again something like a divide and conquer kind of a thing. That's what binary search fits into this paradigm of what is called divide and conquer. Okay, so let's do the following, right? So here is a simple divide and not okay. This is not a divide and conquer algorithm. So, but let's say here is an algorithm which I'm going to say. So insert AI. So I'm going to say for I equal to 1 to n or 2 to n. So what am I saying, right? So it's useful to mention what is called an invariant. Okay, so before I get to this, let's get back to the max finding algorithm because I want to make some comment about it. So what is the max algorithm, which was this was the algorithm, right? How do you prove that at the end of the algorithm, max contains the maximum of the entire input? By contradiction. Okay. So, but here is a let me ask a different question. Suppose I don't go all the way up to n. Okay, it's a big array of n integers, n numbers, and I stop at I going from 2 to 10 and stopped and did the computation. Now, what will max have? Can you, yeah? Let's see. Maximum of A1 to A10, right? The first 10 entries. Can we prove that? Yes, exactly. So we use induction to prove this, right? So first of all, I want to throw in this thing called invariant. How do you prove an algorithm or a program correct? Is you somehow identify an invariant, some property of some variable or something in the program, and you show that it works after every execution of some step. The invariant is maintained, and so at the end of it, using the invariant, you can prove the correctness of the algorithm. So the invariant here, I would say, is that max. So the value at max is the maximum of A1 to I. After, A1 to I, where I is this variable I. So this is true before the execution of this loop. A1, because you have looked at only one entry, it is the maximum. And assume it is true up to the ith step that whatever you have stored is max of A1 to AI. Now when you look at AI plus 1, this algorithm compares it with whatever I have stored, which is a max of A1 to AI by induction hypothesis. So if this is larger than this, then I have updated it. Otherwise, it is not updated because otherwise it is the max of A1 to AI plus 1 as well. Okay. So usually when you want to prove correctness of the algorithm, in this algorithm it's clear, it's intuitive, it's clear that it's correct. But if you want to formally prove correctness, you use what is called an invariant in the algorithm. Invariant in the algorithm is the value stored at the max is the maximum of whatever you have seen up to that point, where we use this for loop to see whatever we have seen. Okay, good. So now I want to use that kind of an invariant argument to say this. So here is my sorting algorithm. So A1 by itself is sorted, right? Because there is only one element. So now assume that A1 to AI minus 1 is sorted. Now I take the AIth element and insert it into the sorted array. How do I insert it? We'll come to that. Suppose I manage to insert it so that including this element, now your new array is sorted, right? So what am I doing? A1 is sorted. Take the next element, do something so that this remains sorted. Right? The do something is what is insert. I'll come to what do you do, right? So at any point of time, if you have some sorted list, you take the next element and insert it here so that this remains sorted. Okay, so that at the end of it, your array will be sorted. Now let's carefully look at what do I mean by insert. What should I do? Suppose I have a sorted array and a new element is coming. What should I do to make the new array including this element to be sorted? What should I do? Do binary search, right? Because if your array is like 7, 12, 15, 18, 21, and somehow the next thing is 6, I want to insert it here. Well, I need to find its position in this sorted array. So let's call it 16, better number. So then I will just do a binary search. I'll compare it with 15, do all that kind of things, and you figure out that 16 should actually. The good thing about binary search is that it will not only tell you your element is not there, it will also tell you if it is should be there, where it should be. So here it will tell you that because your search will end, it will compare it with 15 and realize that it is larger, and compare it with 18 that it's smaller. So I will insert it here and push these things. Okay. So now if I repeatedly do this, so A1 by itself is sorted, insert A2 into that list, A3 into that list, and overall, how many comparisons would I have taken overall?
First step there would be one comparison.
Yeah.
In the second step, because you would have two elements in the sorted list.
Yeah, and generally if I have I elements, how many comparisons?
Log I.
Log I, right? So this is going to be summation log I to the base 2. Right? Okay. And what is this? Clearly this is at most n log n. You can give that. Because everything is bounded by log n. Another way to do this calculation is at most summation I going from 2 to n log I plus 1, right? It can be at most. When you do the rounding, it may become at most plus 1, right? This plus 1s, you can add them to be n. And what is this? You can say it's at most n log n, but can you say a little bit more precisely what is the summation log I? By the property of log, the sum of the logs is what? Log of the product. What are we doing this product here? Or rather 2 to n, it doesn't matter. Yeah. So what is that? Log of n factorial. Right? So this is at most But log of n factorial also turns out to be asymptotically n log n minus something. So overall, net, I have an algorithm to sort if I do this using roughly n log n comparisons, roughly because of the ceiling and stuff. N log n was good. Remember, for our value of n, what was n log n? How many seconds? 40 seconds. Okay. Everybody with me on that? Any? I see some blank faces. Is that clear? Right. So all I am doing, this algorithm is pretty simple. You have some sorted array, take the next element, do binary search, insert it, and make the new thing sorted, and keep repeating it. Okay. So this is an n log n algorithm. Well, there is one little problem.
We need to insert the element in that.
Yes, okay, so we'll come to that. So n log n, remember, is good for our value of n because it's like 40 seconds rather than better than n square. But one catch is we have reduced the number of comparisons, but something else is shooting up. What is shooting up? Okay, let's carefully see what, if I, these are some of the, so let's say I have this thing of I elements sorted. Now my next element comes. I do a binary search and let's say I'm going to insert it here. How do I actually implement the physical insertion in the array, right? I have to move this element here, move this element here, move this element here, move this element here. And then it gets here. So in the worst case, even though the number of comparisons is log n, the number of moves can be n. Okay, so if every time you end up spending this n moves, then overall it's still n square. Okay, so that's now the point I want to make is, at some point I said, oh, I'm going to focus only on comparisons, but maybe that's not necessarily a good idea. So overall runtime is important. We need to check that. Number two, I want to say is that actually there are ways to organize this so that actually insertion will only take log n time, both comparisons and moves also. That takes us to this data structures. Right? So maybe if I really want to insert an element in some ordered set of elements, if I want to do it in logarithmic overall time, yes, it is possible. This is one of the things we will do in sufficient detail later in the course, but that I want to just throw in the idea of why data structures play a role, because if you just simply keep an array, then insertion will actually take linear time, because even though you can do binary search, you have to move elements. But there are other ways to organize it so that you can actually spend only logarithmic time. Okay? So overall runtime is actually n square here. So we have not really solved the problem of getting it n log n, even though the number of comparisons, right? Though number of comparisons okay, quietly I introduced this notation big O. I don't know how many of you are familiar, but this is something we will. Are you familiar with this notation? You've seen it in some other math courses. Okay, so this is something we'll keep using. We will formally define it. So I've thrown a lot of things, right? We've seen two examples or one problem where we saw that if you sort B and then do something, you can do big difference in the running time. I've given you a sorting algorithm where the number of comparisons is n log n, but something else is n square. So it tells you that you have to take a holistic look of the algorithm, not just focus on one operation. You may want to focus on a number of operations. I've thrown you this reason for data structures and also this notation big O. So let's come back to, if I want to design a divide and conquer based sorting algorithm, how would I do it? So I said one of the reasons binary search was log n was that after one comparison, you could just focus on one portion of the array. Okay, you can reduce your range by a factor of 2. But that was to get log n. But here there is no hope. I have to settle for something bigger than n anyway. So suppose, let's say I sort this recursively. Okay, I think some of you suggested this for finding max, but let's say I want to sort, and I've done this portion recursively. I've done this portion recursively, separately. Am I done, or what is the work left to do? Yeah, you have to sort of compare these two things and do something, right? So that is called merge. So what is a merge problem? It has input two sorted lists. Let's say A and B. For now, let's say each of size n. I don't know, A union B or A concatenated with B, whatever, right? So I want to take all the elements and sort them with an extra information that A is already sorted and B is already sorted. Okay. So now, how do I find the maximum element or minimum element, let's say? So this is sorted. Suppose I have these two lists, each one is individually sorted. Now, how do I find the minimum element in the overall list? Compare the two minimums, right? So now actually you can find the minimum in one comparison, right? Earlier when I had no information, finding the minimum or maximum required n minus 1 comparisons. I even sort of argued or told you that you can't do better. But in this case, with this extra information, you can find the min in one comparison, right? How much time to find the next min? Again, one comparison, right? So how do I do? I compare these two and I output whichever is smaller. Once I output, I will move this. and I compare the two sort of the current minimums now and output it. So this will be 7 and this will be, so this pointer movement is nothing but some variable getting updated, right? Remember, you have an I variable going on one list, J variable going on another list, and you compare this AI and BJ. Whichever is smaller, you output it in some K variable moving. I gets updated to I plus 1. Right? So you can keep doing this. Compare the current minimum, output it, and move that pointer right. And at the end of it, you will have your sorted list. And how many comparisons would you have taken so far? Remember, the total list size is 2n, right? N here and n here. So totally how many comparisons? N. Hmm? 2n. 2n minus 1. Why? Because basically, to get one element, you make a comparison. Finally, your output is of less size 2n. So you will make 2n comparison, except that the last element will be free. You don't have to make any comparison, you can output it. Right? In the worst case, two n minus 1 comparisons. Is that clear? Why 2n minus 1? Because I make one comparison, I get one output value. Make another comparison, I get one output value. Now, okay, here is another thing I want to point out. I said in the worst case. Why? Are there times you will actually spend fewer comparisons?
If one of the list is completely less than
Yeah. So, for example, maybe you are outputting only from one list. The one list is exhausted, then you don't have to make any comparisons. You will just output the next array for free, right? So but in the worst case, you will come up with scenarios where you will actually end up spending 2n minus 1 comparisons. Okay. Okay. So this is merging. So now let's go back to our sorting. So this is called merge sort, which is sort the first half, sort the second half, and then since each one is individually sorted, merge both the halves. This is the entire sorting algorithm. How do I sort the first half? Recursively, right? That's the word. Apply the same algorithm, but important thing is you need a way to get out of this loop, because otherwise you can get into an infinite loop, right? So how do I get it out?
when there is a single element.
Yeah, if the size of the list is small, 1 or 2 or 3 or 4 or something, you somehow handle it separately. Otherwise, you do this, right? Maybe 2, sort the first half, sort the second half, merge both the halves. Else, you somehow compare and answer. So now the question is, first of all, clearly the algorithm is correct, because the invariant we will show is that before the merge step, Each one of this is individually sorted by induction, and use the correctness of the merge algorithm to say that finally the list will be sorted. But the big question is, how much time does this algorithm take, right? How do I analyze it? Because it is not as simple as binary search where we said, hey, we make one comparison, range comes down by a factor of 2, we stop when there are only one element, and n by 2 power k is 1, and so on and so forth. It requires more work. We will continue next week on starting with analyzing these algorithms and more formally looking at this divide and conquer algorithmic technique as a paradigm and see how we can analyze these algorithms. Yeah, okay, thank you.